All right. Can everybody hear me? Is the microphone on? OK, good. Yeah, let's get started. So I want to ask something that we all kind of think about. We have to explain to other people. We have to justify many times, right? Is functional programming actually easy? And let's actually do a more specific question. Is functional programming with effect systems easy? We like to believe it's easy. We like to believe that, once you've learned A, B, C, and D, once you've acquired a certain skill set, once you know what things to do, it's like, yeah, now everything is easy. Once we know that we have to make everything a pure value, and once we know that we have to remove all of our immutable effects, or we have to all put them inside of a monad, like we know that that's what we should be doing. But there's a curve, obviously, and the question is, at what point can we consider this to be easy? So, coming to imperative programming, it's relatively simple. You have a sequence of things. You just do this and do this and do this. And OK, so in functional programming, you have to do it differently. By the way, I'm going to put two different sets of APIs at the bottom to show you the functional equivalent API of what would be the imperative API, just so that we have an apples-to-apples comparison. So, right, here's the functional programming equivalent, right? You have to do a flatMap chain. But obviously, this is utterly horrific, and no one would ever do this, so we have a for-comprehension that saves us. But does it always save us, right? So we put our entire application in this for-comprehension, or a set of for-comprehensions that do all of our flat maps, wonderful. But what about the second we need to do branching? All right, what if we need to do branching? Well, that doesn't save us anymore. And imagine that our branching conditions themselves are effects, right? Suddenly, oh, whoops, in order to be able to use for-comprehensions, we need to fetch extra data, because guess what? If transactions are not enabled, then we don't even want to check whether lazy fetch is enabled. This is a typical kind of thing in databases that you have to check. These are effectful calls. They go across the network, very much the definition of an effect, and we don't want to do extra things. OK, so we're back to that. So again, we're back to our nested flatMap chains if we want to be able to do multiple effectful things. OK. And, oh, yeah, by the way, this is like a skill set. Like, you have to know, oh, by the way, on the other side of this, I need to put units, right? Because if these are going to be conditions that are not going to be met, something needs to exist on the other side that is also effectful, right? It needs to be not just unit, it needs to be a ZIO of unit or some effective unit. OK, so what about looping? And this is where it gets fun, right? What if you actually want to loop with some kind of mutable variable? Like, we love to believe that every single while case, that every single looping case in the whole world is just a matter of, oh, this is just iteration. We can have a simple helper function for iteration. But that is actually not true. There are situations where you have to do looping with mutable APIs that you just can't do with simple iteration. So, OK, so how do we actually do something like this using functional programming? Well, something like that. Right? Again, this is a skill set. Like, you have to know, oh, we actually have to recurse into a flat map. Right? We have to flat map into a thing, and then we recurse into there. OK, great. Well, this is starting to get really nasty. Now, OK, you can understand this if we just extract the conditional function and then extract the conditional, make the whole thing into a function, and recurse on that function. We have an understanding of what the equivalent of this thing is imperatively. But OK, still, this is nasty. Oh, by the way, I'm not talking about globally mutable state here, right? The reality is, look, the second that you need to get to a certain level of performance, you need to start having some local mutable state. Let's take a look at exception handling, right? Try catch. It's a language construct, been built in since Java since forever. I mean, this has been around for a while in order to do exception handling. But again, when we learn effect systems, you have to do this differently. And you have to know that, like, oh, on the other side, you can't have something that fails. You have to, like, make it a die failure. It can't have an exception. What if on the other side there's a connection close? Like, what happens if there's a database connection close inside here that could technically also die? Like, you have to know what constructs are available to you in order to be able to do that. So, okay, fine. You have to know. Again, you have to acquire this skill set. And so all of these constructs that we're seeing, they are constructs that were built in by the language. They were built in by the programming language in order to help us, right? Except for, they don't scale horizontally, blah, blah, blah. And so we need to have effect systems in order to be able to do them. And so all of these basic language features, we have to relearn how to do all of them in effect systems. Because, well, we have no choice. Because, again, we want to be able to build horizontally scalable systems, and we eventually have to use effect systems in order to do that. Is this actually necessary, though? What if this complexity is just incidental? What if this is actually a complexity of functional programming that really doesn't actually have to exist? Right? When you take a look at what it takes to go from here to here, is this intrinsic complexity? This is a mechanical rewrite from here to here. This is a mechanical rewrite from here to here, from here to here. These are all mechanical rewrites. So these are incidental complexity mechanical rewrites. What do we do as engineers with incidental complexity that can be mechanically automated? That's what we do. We automate it. Right? That's our job, to automate away incidental complexity, right? So Flavio, who I hope is with us, where is Flavio? Oh, hi Flavio, welcome. He saw this, and he's like, automate this, automate it away. So he essentially wrote Monadless. So he said, I can just automate these code transformations, right? We can code in a style that looks like this and automatically rewrite it to that. So here's one example, right? Let's say you have a sequence. Okay, you start with a sequence like this, all right? Okay, so we need something like this. Now, we don't have this API down here, because we're functionally programming. We have this API down here. So no longer can we return values, we have to return effects. This isn't going to be returning a string, it's going to be returning a ZIO of a string. Okay, what do we do then? We have something called a run function, which is essentially a cut point. It cuts the code out of here, and it knows how to do these cuts and splices it into a flatMap structure. Right? We cut and splice and cut and splice and cut and splice. And metaprogramming allows us to do that. Okay? So then, and by the way, we need like a total macro that does this. So once we have that, essentially, we can cut and splice and cut and splice, create our flatMap chain, return an effect. And then that's it. And then what we can do is we can write code that looks like this and create code that looks like this, right? And this is really close to the imperative alternative. This is really quite close. So, okay. Oh, by the way, we can have a nicer syntax because we can put .run directly as a suffix. Okay. So, right, we could do the same thing with branching, right? We just add all the run calls in order to be able to do the cut points, and then we unify them back into this, right? This is essentially the defer is the equivalent of for, right? This is equivalent to a for comprehension. Defer is the equivalent of for. That's essentially what tells our application, okay, take all of these cut points and splice them back in. Okay, so these are the cut points, right? These are the cut points right here, right? We splice them into a chain that looks like this. And we know, okay, if it needs to be an if with multiple conditions, then we just chain all of the conditions in the ors and ands, right? The conjunctions and disjunctions. We know that we have to splice them into a structure that consists of nested flat maps. This is just machinery. This is just machinery that we have to build that can figure this out. Okay, let's take a look at looping, right? Same kind of thing. We need to have looping, right? We can have a very similar kind of approach. The only difference is that we need to actually execute the cut points first because we don't want to directly read into a mutable variable. Why this is the case, I will explain later, but take this as given for now. You don't want to read into mutable variables. So, okay, once we have this structure, though, again, cut, splice, cut, splice. Let's take a look at exception handling. Okay, again, let's start with something that looks like try catch, right? Define all of the cut points. The run will take all of the effects, all of the places where we have a ZIO of a JSON and we need to translate it back to a JSON, and we just use it, cuts the code out, and splices it into the kind of functional structure that we need to have. So, here they are. So we cut here. Oh, by the way, this thing actually is not a cut point. We have to know in certain cases that you need to encapsulate certain things with an effect just because they begin a block of a defer. Okay, so just more machinery, right? The rest of it are all cut points. We cut everything out in the run function, and we know what kind of structure to splice it into. So this is what Monadless does. It has the machinery in order to be able to convert from something that is essentially imperative code with a bunch of cut points into functional code. Now, by the way, if you're thinking this is an async await solution, this is not an async await solution. We are not awaiting anything. We are not suspending anything. This is machinery for rewriting code. For example, you could have the same kind of approach for lists and queries, right? You can do all sorts of things like that. You can build structures that, at least theoretically, do things like that for any kind of monad. So this is not something that's async await and needs to have like a callback which is on complete somewhere somehow. This is way more general than that. This is a replacement for the for comprehension with more power. That's what it is. It's syntactic sugar. So this is really neat. This is really neat if we could do things like these. And this is what Flavio did with Monadless. And had this library succeeded, it probably would have changed the face of functional programming in Scala and perhaps other languages had this library gotten widespread adoption. Unfortunately, it did not. Whenever some new automation, mechanization, machinery comes into the world, there is resistance. Everything from the sawmill to compiler optimizations, there is resistance to automation and mechanization in the world. And the reality is that it takes a few versions of every single machine in order to work out the kinks and to get it to work right. And while that's going on, plenty of people, it gives them time to say, oh, this doesn't work, this is horrible, this is broken, and even if it did work, I could do it myself 10 times faster. And for a while, people that say that are right, until they're not. Until they're very, very, very not, and then very, 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 very not, and that process goes on forever. The other thing is that when this system came out, there were issues about correctness. Some of these issues were legitimate and thought out. Others were not. And unfortunately, because the loudest of them were not, as is the usual case on social media, the signal of the issue was lost to the noise. However, we are fortunate today. We are fortunate because, Flavio's with us. We are fortunate to have the power of Scala 3 metaprogramming that gives us a paradigm for how safe code rewrites work. We're fortunate to have someone like John DeGoes who is able to see something not only for what it is at that exact moment, but for what it could be, for what it could become. There's a Jewish phrase that goes, "Wise is he who can see what is being born." And finally, we have the ZIO community. We have an excellent community of developers that understand the value of pragmatism and ergonomics over purity and and philosophical purity, ideological purity. And as important as those things are, they can take a back seat sometimes. They need to be in the theater, but they can take a back seat. And this is the story of ZIO. Which is why it is with great joy that I present today the continuation of Flavio's visionary work. This is a system that essentially does what Monadless did, supports all of the basic structures that Monadless supports. By the way, in addition to those four, it also supports match. So you can do match with dot runs on one side and the other side. And also we do basic looping, so there's basic looping support if you want to be able to use that kind of structure. Now, oh, by the way, so there's the syntax, right? That's how you would do basic looping. And if you're adventurous, you can actually turn on a parallel mode that will give you a parallel sort of looping for a structure that is basically a for loop, if you need, again. And this is what I want to talk about today. So let's talk about, first of all, this system is built specifically for ZIO. My goal was to build it specifically for ZIO and not for all the monads in the world. I wanted to focus and get the ZIO features down really well, at least in the beginning before trying to generalize it. And the other thing that I really wanted to do was make it transparent. Make it transparent what exactly the code that's being generated is. Rethink what correctness means, and then also incorporate some other important functionality that ZIO brings to us. So, okay, so let's have a look. What do I mean when I say the system is tailored for ZIO? It will get the environment right, and it will get the error type right. So you use direct syntax, and it computes environment, it computes the error. It knows, okay, we have called directly this set of functionality. This is the environment type that we need. Again, it sees the errors that are happening, and it infers the correct error type. And if there's a union of error types, it understands the union of the error types. There's also a mode that gives you the least upper bound of errors. This is a little bit more experimental, but you can use it as well to be able to have the least upper bound. So all of the things that you call directly, it figures out what exceptions, like the total exception type, the total environment type, and it just automatically gives it to you. Now, this is what you will actually see in metals. You will actually see this in your output signature. Now, we know that metals can be problematic sometimes, and IDEs can be problematic sometimes, and especially with inline transparent types that this thing takes advantage of, sometimes it doesn't get it right. So there's a .info, which first of all will show you the computed type. It'll show you, okay, this is the thing that you need, and if you want to make a type signature, if you want to make a type annotation, this is what you need to put there. Frequently, you will get both. You will get the computed type, and if you do .info, you will get the type that defer is telling you, but they're always the same thing, or they should always be the same thing. But .info doesn't stop there. .info will show you exactly what code has been generated. That is exactly what you will see in the SBT console. You will see, oh yeah, I took this service definition here. Oh, here's the service definition. I've got a second service definition. Okay, it flat maps here into the second service definition. Oh, I have this tuple thing where I have two other effects that I call .run on. Okay, well, that tuple is collected into something, and it splices into another level of the flat map chain. So it will tell you. This is not as simple as it potentially could be. We have to make some copies of certain variables occasionally, just because otherwise compile times would be much slower, so there are a few caveats like that. But anyway, this will show you essentially exactly the code that is being spliced. We have several layers of verbosity that show you certain other things that you may or may not care about. And on top of that, we actually go even one level further. And you can actually see how the system works internally. You can see the scaffolding that the system constructed from your original structure. So it sees, oh, okay, there's a block here that we're going to run. There's another block here that we're going to run. If there are any vowels, it sees that. So as much as I can, I'm trying to make this thing a white box. So this is not something that you just need to trust and trust that it does the right thing. No, you can really look inside and see what it's doing fairly easily. Now, speaking of which, by the way, how do I just splice multiple effects on the same line? How do I just do that, right? Don't you need to flatMap across them? Right? Well, I take advantage of things like collect all. And what I do is I extract all the effects into the collect all, run them, and then splice them back into the code. This is one of the great insights of the Monadless design. And again, you need to make the assumption that on the same line you will not have mutation. That every single effect that gets called on that line only affects other effects, but not other things that you're splicing in here, which means that the paradigm is that all of the code inside of a defer needs to be eager and immutable. These are the things that you need to keep track of. And it can go very wrong if you start doing mutable code inside of this, right? Let's say you need to lock a database row before you use it. Well, if you do something like this, it will actually do the effect before the lock, because it'll actually do the row read before the lock. Because right now, the effect happens first. So again, do not do mutability outside of effects. And if you just follow that recipe, do mutability in effects, then everything will be fine. That's the correctness guarantee. You need to make sure that mutable things and lazy things are done inside of effects, which is what we teach. Right? Which is what we teach in effect systems. Do mutability in effects. This is the right kind of thing. And again, you will see the code that's generated. Right? You can not do things in mutable blocks, and this will actually work. By the way, this is not the code that gets generated. This is the code that gets generated. So you can actually see the generated code is correct. It will actually check the next row first, because it knows that if there's a conditional, irregardless of anything else, you have to run the conditional first. So it will generate the right code, even if you do the wrong thing in the vast majority of cases. But again, just follow that recipe. Mutable things and effectful things, do them inside of effects, and you just can't go wrong. So, this is another example, right, where you can try and, this is really nonsensical at this point, like trying to yield a tuple with multiple mutable things. But again, you can really mess around with mutable structures. This is the problem with correctness. This is why for-comprehensions are structured the way they are. Trying to do mutable things is problematic outside of effects. This is 101 of effect systems. So just use effects to do them, and everything will be correct. Now, what's the basic insight here? The basic insight here, again, so we understand in effect systems that a sequence is a flatMap chain. Now, when you are doing multiple things inside of the same line of code, and when I say the same line of code, I mean two things that if you wanted to put on the same physical line, you'd have to do a semicolon. Right? Like that's why the semicolons are there, ultimately, to separate statements. Now, Scala allows us to pretend that they don't exist because we can use return characters and other things. But again, like a single assembly of a tuple, a single assembly of an if statement, we know where the boundaries of these things are. So when we take all of these and we extract the effects, there is an understanding that this is a single block. And on this level, we can do things like that. Now, right, because essentially sequence running forward from left to right and from up to down, right? In functional code, it runs, the next sequence is always on the other side of the flatMap. So whatever we're doing, whether it's left to right or up to down, it's on the other side of the flatMap where the effect of that actually has to go. And again, that's the basic law of correctness. So Sequentiality in imperative programming is nesting in functional programming. So you just, that's the paradigm, right? That's the paradigm of the for-comprehension. So, by the way, these are the rewrite rules. I won't go through them, but they're not that complex. Like, at the end of the day, the rewrite rules of the system are not like some insane thing. So again, I have actually made all of the things, as much as I can, I have made all of the things that could break this illegal. And because I have all of these constraints, that's where I'm pretty darn sure that all of this is correct. Right? If you try and do assignment, I will immediately throw a compile time error. You will not be able to compile your code if you do this. Same thing with mutable variables. All the problems in the world that happen with assignment also happen with mutable variables. I will not let you compile the code if you do this. Right? Now, of course, you could extract these things into other functions, and then I don't know what's going on because it's opaque to me, but okay. Right? There are limits to what I can do. But so the idea here is that just take all of these mutable things and extract them into effects, and everything will be correct. That's it. Just extract the mutability, extract the interactions with outside state into effects. This is, by the way, I've got to go on and talk about some of the arguments against this system, because there have been many arguments against Monadless, and probably the one that I think is least thought out is this one. Essentially, oh, it's non-referentially transparent. You know, in functional programming, we believe very highly in referential transparency. That's like the creed that we have. Every single term should be replaceable with every single statement should be replaceable with a value to which that thing is written. That eventually becomes interpreted as the order of statements shouldn't matter, which is actually not the same thing. It's actually more commutativity, but anyway. So we have these principles, and so the issue that a lot of the critique in Monadless was that, oh, if we rearrange the order of terms, the outcome is different. This was the idea, and because, right, you rearrange the terms, it's not referentially transparent. But here's the thing. These are not real values. This int, this bool, these are not real values. These are syntactic sugar. Here's the reality. Here's the reality. Now again, this system right now, ZIO-Direct, does not support using lists. So this makes this example a little bit theoretical. But Monadless, this was a functionality that Monadless could do. So again, it's just syntactic sugar. This is not async await. These are not real values. This is sugar. This is the same thing as a for-comprehension, right? These are not pure values, right? These are not pure values. Oh, but the left-hand side doesn't have a monad signature, right? Like, that's the argument. The left-hand side doesn't have a monad signature, right? These look like values. Well, for-comprehensions are the same thing. The left-hand side doesn't have a monad signature, but that's an aspect of the syntactic sugar. There's a difference between syntactic sugar and programming paradigm, right? This is just syntactic sugar. This is not an async await system. These are not pure values. Another version of the argument tries to move that value down there. Yet another version of the argument tries to rearrange the values with dot runs and say that, oh, if you rearrange the values, it's different, therefore it's not referentially transparent. If you really want this to work, just move the run calls down there. Just move the cut points. You move the cut points down there to where you're actually doing the cut, then you can rearrange the stuff above in whichever way you want. Anyway, so, right, let's, this is another sort of thing where, you know, this is actually a well thought out argument. This is a well thought out argument. This is like, look, what are the laws? What are the laws, right? If we say that suddenly the dot run function makes everything co-Kleisli, what are the laws? These are the laws. Here are the laws, right? Ye shall not use mutable things inside defer. Ye shall not use pure things inside of a defer. Ye shall not interact with external state inside of a defer. All of the effects will be run from top to bottom, left to right. All of the things in between the effects will be run in between the effects. The only difference is, again, on a single line. The order of things that can run on a single line can be different. So here are the laws. Here are the laws. Oh, and by the way, we know every single kind of thing that can exist in a line of code. This is not arbitrary structures. Like we have an understanding of every single thing that can exist inside of a line of code. But anyway, let's talk about error channels for a little bit. Let's talk about something a little bit more pragmatic. So we have this understanding in ZIO that there are error channels, that there is a success and that there is a failure, and that there's ZIO.succeed that is supposed to have pure code, ZIO.fail, which is supposed to have error types. But if you have code that throws an exception inside of what should be pure code, right here, this is essentially a die failure. Right? This is a die failure. So, okay, fine. But what happens if you expect exceptions to happen? So we have something called attempt or effect or a couple of different names for it. But the idea is we expect errors to happen here somewhat. So, but here's the thing. If what goes in a defer is pure code, and if you throw something inside of a defer, it by definition has to be pure code, which means it has to be a die failure. It can't go through the regular fail channel. So what do we do if we want it to be going through the regular fail channel? Well, you could just do this, right? You could just do a ZIO attempt and do .run. That's fine. That's pretty reasonable. But because I expect this kind of structure will be very, very, very common, I have this unsafe thing that allows you to encapsulate that. And by the way, what's nice is that if you have this kind of structure where you're just reading a bunch of things from effects and interacting with the values that are sort of coming out of those effects, and potentially multiple things can throw exceptions in order to have this experience where every single thing inside of this block, inside of a block of code, could potentially throw exceptions, and we just expect that to happen. Right? These are all the things that could potentially go wrong. Yeah, you could wrap all of these inside of unsafe, but you can also wrap the whole block in an unsafe, and it knows to put all of the things inside of here that are not effects, to put them into ZIO attempts. And it understands that we have to do that. Oh yeah, by the way, just like the environment type works correctly with the system, scoping works correctly within this system. So if you do something like use a call that returns a ZIO with a scope, the scope will be propagated correctly. Just FYI. And oh yes, by the way, so when you do this unsafe thing, right? Notice how without unsafe, it actually opens up an input stream reader, prepares a connection, right? These are things that can throw I/O exceptions. It wraps them inside of ZIO attempt. It understands, walk through the tree, see all of the different things that are not happening, that are not already wrapped in effects, wrap them in effects. And the last part I want to talk about a little bit is mutable refs, right? So mutable refs we like to use whenever we need a stateful variable. And we understand that, okay, if we try and maximize the capabilities of values and things that don't allow for mutation, our use cases for mutable variables will be radically decreased. But this is not always the case. They're not eliminated. You still have plenty of difficult situations that do require some kind of mutable variable. Sometimes they're thread locals. They could be a variety of things. But the second that you introduce these kinds of mutable refs to functional code, to effect system code, things get nasty very, very quickly. So here, for example, again, this is a little bit contrived because I'm just doing iteration here. But if you really want to make it equivalent to something like this, again, you have to have a function that flat maps into itself, and as it flat maps into itself, it calls the result of the mutable ref. And by the way, if you put this function up here, the whole thing will run forever. So this is actually quite error-prone. Mutable refs are complicated. This is what the defer of that looks like. This is mutable refs. Essentially, this structure allows using mutable refs with almost the same ergonomic properties as mutable variables. This will generate the correct code with mutable refs. You can almost treat them as a variable. That's, I think, if anything else, if you're using mutable refs, you will love this system because they treat mutable refs very nicely. And yeah, by the way, here's the code that'll return, right? Again, it's just a flat map chain. It's just a flat map chain, but you don't necessarily always have to think about it. Here's a quicksort. Here's a regular mutable quicksort, right? Here's a quicksort with mutable refs for the indexes. I can also store the array in a mutable ref, but it'll be uglier. Again, just try, as an exercise, try writing a in-place quicksort with mutable refs. I mean, I don't actually suggest you ever run something like that in production because the constant time factors of that are horrible, but you can actually do it. It will be comprehensible, right? I don't think this is really possible right now. I think that trying to write something like this with, I mean, I attempted it for all of 10 minutes, but writing something like this with mutable refs is just a complete and utter nightmare. So I guess that's it. ZIO-Direct allows direct style programming with ZIO-FX and interoperates with ZIO error types and interoperates with ZIO environment types. You can actually look inside of this thing. This is not a black box. You can look inside to see what it's doing. It tries as much as it can to blow up if you're doing anything incorrect. If you're doing anything that involves some kind of mutation, as much as I can, I try to say, no, stop. Please don't do this, or do this inside of an effect. Uses the ZIO error channel correctly, and with things like mutable refs, where the result is always on the other side of a flat map, it'll really be a nice experience. And by the way, oh yes, future directions. Eventually, we want to have this thing work with other data types, with other structures, and support other kinds of things. Again, in order to write this, I had to specialize it for ZIO. In order to get the environment types and the error types correct, I had to specialize this for ZIO. This is one of the future directions, and to be able to essentially support other kinds of monads. But anyway, that's it. This thing is released. It will be released in a few minutes. It is on RC1. It's in a relative state of completeness the way it is right now. Just because, in fact, I have a branch right here where I took the ZIO context of protoquill and I rewrote all of the uses of for-comprehensions using ZIO-Direct. And it works. It's not, there isn't anything major. In fact, as I wrote it, I was expecting major explosions to happen, but they didn't. And so that's why I think it's relatively solid. So if you're interested, and especially if you have mutable refs that are driving you crazy, have a look at this. FYI, right now it is only supported for Scala 3. We will have a Scala 2 version, hopefully in a couple of months. And that's it. Thank you.